This is BBC Scotland, Broadcasting House in Glasgow. In one of the television studios, they're making a programme called Agenda.
Brian, are you happy on the floor now? Yeah. Right, OK, stand by, please. Can we run VT? Right, 9, we're on titles.
8, 7,
stand by studio voiceover.
5, 4, 3, 2, 1, 0.
It's a current affairs programme giving a distinctly Scottish angle to the news of the week.
But first, the Scottish Grand Committee, which meets for the first time tomorrow in Edinburgh. The committee will...
Everything that happens in this studio is directed from the control room upstairs. The rows of television monitors show different pictures which can be chosen. 3 of them come from cameras on the studio floor. But this programme takes pictures from other sources too.
The town was previously employed was ludicrous, and the press have
Parts of it are pre-recorded, on film and videotape.
And a Tory poodle.
Morale at the board recently has not been good, and Cowan's first priority is to court his staff.
One of these videotape machines has an item about the Highlands and Islands Development Board. And the other's being used to record the final programme. These machines are 100 yards away from that studio. Today they're linked to it by sound and vision cables. Tomorrow they could be doing something quite different. There are 2 television studios here in Glasgow. They can be linked to videotape recorders, to film transfer machines, or to the main BBC television networks. And they can also be connected to transmitters throughout Scotland. So there's a lot of electronic equipment to link together, and this is where it's done. This is the switching area. It's like a telephone exchange, with these fat cables sending television signals from one part of the building to another. But this equipment's getting old, so a new computerised switching room is being installed. It'll deal with the routing of all the television signals in this studio complex. And it'll also deal with radio, linking several sound studios with the BBC's radio networks. But we're not so concerned about what this new switching centre will do. We're more interested in the problem of getting it built. Computer systems can be used in the management of complicated projects like this one. One technique that's used is critical path analysis, or PERT, P-E-R-T, which is project evaluation and review technique. One special feature of PERT is that it uses a complex data structure, which is called a graph or a network. This network represents the structure of a project spread across time. The different things that must happen are laid out on diagrams like these, together with relationships between them. For example, install video monitors. In an installation this size, installing monitors is more than just putting in a plug. There are several cables connected to each monitor. They contain synchronizing and test signals, together with 3 colours, red, green and blue. The cables must be laid in position before the monitors are moved in. With dozens of monitors, it's a time-consuming task. And that's shown on the network. Install video monitors. It's called an activity, and this activity is scheduled to take 2 weeks. Installing is followed by testing. Each monitor is checked to see the picture isn't twisted or the colours incorrect. Not just once, but over a period of time. So that's a second activity. In the network, the 2 activities are separated by an octagon. That's an event. The finish of one activity and the start of another. Events have code numbers for identification. This one's VS0044. And this event is followed by the activity of testing the monitors. This project is in 3 parts, with around 200 events in each. That's why it needs to be handled by a computer. Project leader Norman Bennett.
I find these networks very useful indeed, because on a large project like this, it's very, very difficult to keep track of a multitude of activities, many of which are interrelated. And for example, if I see on this network a red line, for example here, in video incoming line equipment is shown as red, then this indicates to me that this activity is critical. There's more information inside the computer than is shown on this network. For example, there's an activity here, install video monitors, JRP, that's John Passfield, one of my engineers, and a wireman. Now I may have a parallel activity also with a wireman, and these are known as resources, and therefore I will have to resource for 2 wiremen. I can see this easily from a bar chart produced by the computer. It's a wireman schedule, and each solid bar shows where a wireman will be needed. That's called resource analysis. And it uses information from the computer to predict how much of each different type of resource we're going to need at each stage of the project.
So there's a lot of detailed information stored in the network. Let's see how it gets there. Each project leader has to prepare information for his own network. He uses his experience to say that some activities must precede others. Installing the monitors must come before testing them, so that's included in the sketch. And so is the estimated duration.
250:MS.
Once that's done, the data can be entered at a terminal.
Microprocessor I/F space-space.
The network isn't entered as a diagram. Instead, each event's given a number.
A:/MS 0705:MS 0730 up arrow.
MS refers to the part of the project. It stands for miscellaneous systems. The number identifies the event.
Space hardware delivery up arrow CNM space.
Each activity is identified by 2 events, before and after.
0730:MS 0735.
And then more information about the activity can be entered. To start with, information about each activity is stored as a record in a serial file. In each record, 2 fields contain event numbers. The preceding event, in this case VS0044, VS stands for Video Systems, and then the succeeding event, VS0500. The next field describes the activity, Test Video Monitors, then the duration of the activity, 1 week, and finally other information relevant to that activity. When the file is created, the records are added one at a time as the information is entered. They're not in any particular order. So once the file is complete, the first stage of processing reads the records into Working Store and checks that they make a logically consistent network. For example, this record's for an activity starting with event VS0425. So there must be another activity finishing with VS0425. If there isn't, and this isn't the very start of the project, then there must be something missing. This isn't very clear if we just look at a list of records. It's much more obvious if we draw them out as a network. Each record represents the link between 2 nodes. Another record, with an event in common, is joined onto it. And in this way, we can build up the whole network. With this sort of representation, you can see how to check the records to ensure they're consistent. For example, you can't have this. Activity A must be finished before B starts. B must be finished before C starts. and yet C must be finished before A starts. That's called a loop, and if activities form a loop, there's obviously been a mistake. And you can't have this either. This new activity just starts. It isn't connected to anything else at the beginning. It's called a dangle, another kind of error in data entry. But if the two checks are satisfied, the processing can continue.
You turn the power off, Martin.
But what you see on the network is only part of the story. Resources are important too. Charlie McCaw is one of 6 engineers working on the project. He looks after all the microprocessor systems which control switching. That includes testing each section to iron out any faults.
I'm getting transmit data, no receive. Definitely a fault on this card. Can you power down again, please?
Because of their specialised knowledge, the engineers aren't interchangeable. Each man's workload must be evenly distributed.
Make sure it doesn't break, okay? Otherwise we have to rerun the cable.
But the actual installation work is done by wiremen. They follow instructions and move easily from one part of the project to another. This man's wiring up communication links. But tomorrow he could move to a different part of the project. So there's flexibility with the wiremen, which makes scheduling easier. Let's see how it's done. Here's part of a small network with just 4 events. We'll refer to the activities by the numbers of the corresponding events. Activity 4.7 has duration 3 weeks. We'll show that underneath the arrow. And we'll show the duration of the other activities too. The 2 lower activities are comparatively long, 6 weeks and 5 weeks. We'll mark them in red to show they're critical, and we can see what this means from a bar chart. The bar chart is like a calendar, laid out horizontally with week numbers across the top. Activity 4.5 starts in week 1 and lasts for 6 weeks. It has to take place then. That's what we mean when we say it's critical. The same goes for activity 5.8. It can't start earlier than week 7 because the preceding activity won't have finished, and this activity must be complete by week 12. But what about activity 4.7? It can't start earlier than week 1, but it could start as late as week 8. If it does, it'll finish in week 11, leaving 1 week for activity 7.8. This extended duration when the activity could take place is called a float. The activity lasts 3 weeks, but could take place anywhere within a 10-week range. So there's a float of 7 weeks, representing slack in that part of the system. Activity 7.8 also has a float. If activity 4.7 ends as soon as possible, then activity 7.8 could start in week 4, though it needn't finish until week 11. So how can we schedule activities with floats? That's where resources come in. Look back at the network. Activity 4.5 is supervised by one of the engineers, CM. That'll be a full-time job. But the same engineer has to supervise activity 4.7. He can't do both at once. So on the bar chart, activity 4.7 can't start until activity 4.5 has finished. That's week 7. And then activity 7.8 must wait until week 10. That information's a consequence of resource analysis, and it's invaluable for the project leader. Of course, paper schedules have to be compared with reality.
Can we move on now then and progress the microprocessor system? This is principally you, Charlie, on your PERT chart. The first activity here, design output modules.
Yeah. Well, along with Paul, we have got about halfway through that. We're just sort of getting the prototypes on breadboards, so we have to finalise that design, so there's probably another couple of weeks left there.
So there's 2 weeks outstanding.
Yes. On that one.
How about...
There must be regular checks to see whether all the activities are completed on time.
We're doing quite well there. We've got some action out of drawing office this time, and we should just have to modify that when we've tested the prototypes.
Now,
This meeting raised several problems for the project leader.
at our regular progress meeting last December, we found that we had problems with our microprocessor-based switching system, in that some of the activities were running late. In particular, delivery of printed circuit boards was coming out as 24 weeks duration, which was unacceptable to us. And the result of this is that activities at the end of the project were being pushed backwards, and the chart looked pretty catastrophic. And as we can see, some of the activities should have started here earlier, and in fact they were running 8 weeks late.
One advantage of a network is that it's easy to find the bottlenecks in a very large system. One major bottleneck was here, delivery of the printed circuit boards. So Norman Bennett rearranged his network. He introduced a new activity with duration 24 weeks. And once he'd decided on the changes, they could be entered at the terminal.
And then he wants to add an activity later on, which is A colon MS 0705 colon MS 0254. Deliver outstanding Zeus boards.
This is the new activity.
CNM.
And here's its duration.
24. Colon MS 0720.
And this is the result on the network. A change to this activity. Only the prototype boards will be delivered, and the duration will be reduced to 5 weeks. The extra activity is here. This is the one which lasts 24 weeks. And this is the processing involved. Each alteration is stored as a record. This one's the change. And this one's the addition. Once the alterations are stored, it's just a standard batch processing run. First a sort into event order, and then the update stage. Records are transferred to the new file. This record to be added is transferred to the right place. And this one, to be changed, has the necessary alterations made to it. Then the resulting file can be processed to give the new network. And with the new schedule, Charlie McCaw's life is much easier. The new arrangement means that the prototype boards will be delivered on time. You'll be able to evaluate and test them. And it won't matter that the remaining boards will be 24 weeks late.
On a large project such as this, some changes take place during the course of the project, and changing just one minor activity can have quite unforeseen implications on activities further down the network, which in effect would then jeopardise the completion date. And if the completion date goes back, then that costs us money, which is unacceptable, of course. And that's why I consider PERT networks essential in monitoring projects like these.
OS1, a videotape machine, VT2 as you've chosen.
When the project is complete, these VDUs will automate the control of the switching of television signals here in BBC Scotland, replacing those bulky cables.
The operator assigns ASN space VT2 and enter STB, Studio B.
It'll be an easier system to manage and maintain.
VT, enter, and
And it happened on time because the project leader used a critical path network to help him manage effectively.